As I mentioned, we are starting chapter 3 today, and the topic is arithmetic for computers. So let's start with that. The things that we're going to cover, we're going to look at operations on integers, so addition and subtraction, and this should be a review for you from ENG 312. We also are going to be looking at multiplication and division and different implementations of that. And that's going to be mostly new to you. We're going to be talking about overflow. We have talked about overflow in the context of the ISA, and now we're going to look at that, how it gets generated in the context of the actual arithmetic unit that generates it. And then we're going to look at the floating point format, the IEEE standard for floating point formats, and that is new to you, and we're going to go through the format and the representation and operations of it, including the implementation of arithmetic for floating point, which is much more complex than the implementation for integers. And for example, you know that some processors may have only integer arithmetic, and some may have a floating point unit if you're dealing with embedded processors. So let's start by looking at an example that again should be review for you. But we're going to be pointing out the generation of overflow. So the definition of overflow is that the result of an arithmetic operation does not fit in the storage provided. So the big picture here is that when we're dealing with hardware, we always have limited storage. And we have said that as a matter of specification. For example, we can say the word of the data path of this piece of hardware is specified to be 32 bits. So that is the limited storage. We can only represent values that fit in 32 bits. And if we have an arithmetic operation that is operating on two valid, in this case, in this example, 32-bit numbers, but the result does not fit in the 32-bit number space provided, then we have an overflow. So that is the definition of the condition. So when can that occur? Well, certainly if we are adding a positive number and a negative number, meaning that we're really doing a subtraction, the result is going to be smaller than the operands. So we're guaranteed not to have an overflow. However, when we are adding two positive numbers, the result can be larger than either or both. Well, actually be larger than both the operands, and then we'll have an overflow, or we could have an overflow if the results are larger than both. And if we are adding two negative numbers, negative numbers, we can have an overflow on the negative side. So that's the case where the result is more negative than both the operands, and therefore we can have, if it doesn't fit, again, in both cases, in the storage provider, we will have an overflow. On the case of two positive numbers, this happens if the result sign is 1. So overflow results are also erroneous. Not only they don't fit, but if you look at the result, at the value in the context of the storage provided, it is the wrong value. And the same applies to the case of two negative numbers. The result not only is not going to fit, but it's going to be erroneous. It's going to be the wrong value. And we know that because the sign bit for an overflow when we add two positive numbers is 1. So clearly, if we are adding two positive numbers, the result cannot be negative, which is what a 1 in the sign bit implies. And if we are adding two negative numbers, and if we have an overflow, the sign bit is going to be 0, which implies a positive number. And of course, if we subtract or if we add two negative numbers, the result cannot be positive. So now this gives us some insights to look at conditions at specific bit values to detect overflow. So we know that if we should have had a positive value, but the result is negative, that's an overflow condition. If we should have had a negative result, but the sign is 0, then we have an overflow. So let's look at some examples. Let's say that we have the number 7 and we are adding that to the number -6. So we can see here that -6, or I'm sorry, we can see here that the result is 1, so that fits in the range. So we don't have an overflow in that case. Here are some other examples. So 7 plus 1. If we are talking about using 4 bits, how would that look? Oops. How would that look? So 7 would be, if we're using 4 bits, 0, 1, 1, 1, and 1 would be 0, 0, 0, 1. If we add that, we get 1, 0, 0, 0. But that's -8 if you have your storage is limited to 4 bits. So the result produces an overflow, or the operation produces an overflow. How about -6 and -5? Well, that's going to be -11, which clearly doesn't fit in 4 bits because the highest value on the negative side that you can have is -8. How about 6 minus -7, which is 6 plus 7? Again, that's 14, which doesn't fit in 4 bits because the highest positive number that we can have is 7. And the same goes here for -11, which gives an overflow because, again, the highest negative value that you can have is -8. So the concept of limited storage is important because depending on the application, you can have, by specification, different limitations on the length of the storage that you are using. For example, let's take a look at arithmetic for multimedia, specifically for graphics, video, audio. So the normally you can represent with high resolution imaging and video with 8 bits of data. If you use 8 bits for each channel, red, green, and blue, that gives you overall 24 bits of colors, which is essentially about 16 million different colors for each pixel. So just with representing each channel with 8 bits is sufficient. Audio, you can have CD quality audio with 16 bits of data. That gives you about 64,000 levels, distinct levels of audio. And if you really wanted very high quality audio, you can go up to 32 bits, and that's obviously about 4 billion. But 16-bit is more than adequate for good quality audio. But from a computational perspective, we have this hardware. Let's say in the ARM that we are studying, we have a data path that is 64 bits. So how can we leverage the hardware that we have to actually speed up the computation of multimedia type of data? And this is what is called single instruction multiple data type of organization, where we can have a multiplier, which is a 64-bit adder or a 64-bit multiplier. It really doesn't matter. It's in general the hardware for the arithmetic to be partitioned so it can do parallel operations with the same hardware by just using some logic to reconfigure it, depending on the type of data that is using. And that is called vector processing. We'll talk some more about that later on. But if you have a 64-bit adder, you can do one 64-bit addition, or you could do two 32-bit additions at the same time, or four 16-bit additions, or 8 8-bit additions at the same time with the same hardware, because you can partition, essentially the carry chain can be restructured so you can do this. So again, the other point is that a multimedia data that is going to really be consumed by the senses of humans, overflow is not such a big deal. I mean, you don't really want overflow when we're doing scientific computations or financial computations, but something that is going to be consumed by the senses of humans, we're very tolerant to that. And additionally, we can add hardware to change the overflow condition to something that we call saturation. So instead of giving you that wrong value, it just gives you the highest value on either the negative or the positive side. So how does that look? Let's say in video. So basically it saturates. It saturates the color of the picture. Let's say if we're talking for simplicity about all three channels, the pixel is going to saturate at white or black. Those are the extremes. So that's okay. That may be some artifact in the picture or the video, but we can tolerate that. On audio, it translates to essentially a pop or a click that you can hear, but it's not terrible. I mean, nothing is going to happen if there is that artifact on what you're listening to. So in multimedia, we have not only the saturation or the overflow being translated to saturation, but also we have the ability to do vector processing on wider number of bit arithmetic units. Now let's take a closer look at multiplication and start doing what you would do on paper, and then let's see how we can translate that to hardware. If you look at what you would do to multiply two 4-bit numbers, you're essentially multiplying this one on the top by each bit on the second, and just writing the result aligned with the bit that you're multiplying by. So this would be 1000 times 1, I get 1000. 1000 times 0, I get 0000. Again, 1000 times 0, that gives me 0, and 1000 times 1, I get 1. And then I add those numbers, and this is my result. Okay? This is my result. These numbers here are what is called partial products. They're partial because they contribute through addition to the result later. Furthermore, if you look at this partial product generation, what you're doing is ANDing each of the bits. From an actual hardware perspective, you are ANDing each of the bits of this number with that one bit. And that's how you generate the partial product. So the partial product generation is an AND function. And we have hardware to do that. Then once I have generated my partial products, I have these shifts that have occurred. Well, that's just moving the wires, in this case to the left. That doesn't even require hardware. And then I have the addition, which I know how to do. Worst case, I can add two of this at a time. I can add this two, then add that one, then add that one, I get my result. So you can start seeing how I can design a hardware multiplier from a logic design perspective. I can also take an algorithmic approach and design a multiplier that does that process, but it does it sequentially, meaning on a clock. It's not doing it. You could certainly do everything in parallel, just have all the partial product generation done and all the addition. There is no sequential logic there. It's all combinational logic. So you could have a single cycle multiplier, but you could also take an algorithmic approach. Going back to the concept of the ISA, if your ISA offers a multiplication instruction, that is the extent of the specification from the hardware-software interface. Whether you implement it as a parallel multiplier or a multi-cycle multiplier, that's an implementation detail. And again, that's the importance of the ISA, that it allows you to keep the interface to the programmer constant while you can do different implementations. So in this picture here, we're seeing a raw implementation of a multi-cycle multiplier or an algorithmic multiplier, this controller is a state machine. And we start with the multiplicand, which is the top number, and the multiplier, which is the next number. And let's say that these are 32-bit numbers. The multiplicand and the multiplier are 32-bit numbers. Also know that when you multiply two numbers, two binary numbers of any number of bits, so if I have a number of bits in my multiplicand and b number of bits in my multiplier, the result, the storage that I have to provide for my result needs to be at least a plus b number of bits. If they are the same number of bits, then the result is twice the number of bits. So this is why we have here a 64-bit is an ALU, but it's really an adder. And we have a 64-bit adder. If we have 32-bit multiplicand and 32-bit multiplier, and the product is going to be 64 bits. So we're going to provide here a 64-bit register for the multiplicand because we're going to be shifting it left. And we could shift it up to 32 times, so that's why we need the 64-bit register. Here, we start with a 32-bit register for the multiplier, and we're going to be shifting it right. But once we look at the least significant bit to generate the partial product, we don't need that bit anymore. We don't need that bit anymore. So we can shift right and just lose the bit. And we start to the same process, looking at the least significant bit of the multiplier, and then if it's 1, we're going to add the multiplicand with the product. So we are already accumulating the partial product, starting with the product at 0. And if the least significant bit is 0, we inhibit the multiplicand and just add 0 in that clock cycle. And then in any case, we shift. And the product and the process repeats itself 32 times, as many bits as we have in the multiplier. So that's why this is controlled by a state machine over here. So you can build this multiplier. You have your, in the same organization discipline that we have been discussing in the lab, you can see that you have a data path and you can have a control. State machine and registers, adders, shifters, so that are controlled by the controller. What are your outputs? The product is the output of this, and the inputs are the multiplicand and the multiplier, which you can latch into the registers at the beginning of the process. So that is a raw implementation of a sequential multiplier. And here's your algorithm, which is just what I articulated previously. Okay? So let's look at that, how that design would work. for 4 bits, of course. So here's our multiplier in the, let's say that this is in the 4-bit register, and our multiplicand in an 8-bit register, just like our 32-bit multiplicand was in a 64-bit register. So we look at the bit and we add it, essentially. So it starts with that value. So now we shift one right and the other one left. And we look at the bit. And we're going to add it. And we shift again. We look at the bit and we add. That zero function is essentially inhibiting the adder from passing through the multiplicand from, in the previous picture, the 64-bit register. Then we shift again, we look at the bit, and we add. Now we've been adding all along in the architecture that we showed. So let's just do that now, and we get our result. Now we can look at that hardware and we can provide some optimizations. So we can look at the original that we had, and we can see that we have this storage over here that is empty to begin with, but it doesn't matter where we shift the 32 bits inside the 64-bit register. What is valid is only the 32 bits. Okay? And then this multiplier over here, we're using 32 bits, but we are discarding it. So at the end, we end up with this register being empty. So there are some ways to look at that and optimize the storage, also recognizing that even though we are going to get a 64-bit product, that's an effect of the shifting. But the actual addition, the relevant addition, is still 32 bits. So we can simplify this by making those observations and starting with a multiplicand stored fixed in 32 bits. But adding those 32 bits into a product that is already pre-shifted 32-bit times. So in essence, we have pre-shifted, we speculated on the shifting, and then we're going to shift back if we were wrong, depending on the bits of the multiplier. If we're going to start here with a 32-bit addition into the upper 32 bits of this register, the lower 32 bits of what eventually is going to become the result is empty. So I can use those 32 bits to store the multiplier because I'm going to be shifting it and discarding anyways. So in this architecture, we start with the multiplicand in this register, and we start with the multiplier in the lower 32 bits of the product register. So we saved already that we don't have this register, so that's a savings. And the other big savings is that instead of a 64-bit adder, I have a 32-bit adder here. And we're going to do the same process. we're going to look at the bit, and if it's 0, we inhibit, and if it's 1, we add into the upper 32 bits, and then we shift right, the whole thing. We have to shift right because we pre-shifted by adding into the upper 32 bits. It's like we pre-shifted 32 times the product. So we have to correct that. So we shift right, the whole thing. But remember that here we have the multiplier. So now we look at the next bit and we do the same thing. So that's a demonstration how you can look at hardware and look for optimizations if you're clever, and you look at what is being, how to optimize the utilization of the hardware. So that's a multi-cycle multiplication that for 32 bits will take 32 clock cycles, and it's a very economical implementation versus the parallel multipliers that are fully combinational and replicate the logic for partial product generation and replicate the others. So if you just need a multiplier and you can afford to wait that many cycles, that's okay. That's a very economical implementation. So let's go through this with the optimized, what we call the optimized multiplier, the second version. So here we are. This is the multiplicand, and this is in 4 bits. This is the multiplicand, which is in the upper register, and the multiplier is stored in the lower half of the product register. So you look at the bit, and you add. And you keep doing the same thing. You shift. So you look at the bit, and you inhibit the addition, and you shift. Again, you look at the bit, the least significant bit, and you add, and then you have your results. After the shift, after you do as many shifts as bits are in your operands, you have your result. So after the 4th shift. Okay? I don't the carries here are inconsequential. But you do store them because you need your shifting. So you need, if you do have a carry, then you use it for the shifting into the product register. So that's a 4-bit example of how that second version of the multi-cycle multiplier will work. Okay, so let's talk about, now that you saw these multipliers, sequential multipliers that take multiple cycles, how can you make fast multipliers and you don't get anything for nothing? You have to, there is a trade-off, and the trade-off is in complexity and the cost of hardware. And you should know already from what we discussed at the beginning that is going to involve the duplication of hardware are mainly the adders. Okay, so if you have many bits, you're going to end up with a lot of adders. So in this case, when you have a 64 by 64 bit multiplier, even though you have even though you're doing 32-bit addition, remember that the pertinent addition is 32 bits, you end up with this tree of adders or 32-bit adders that is quite extensive. And what we have here are the partial products. So again, if you're multiplying two 32-bit numbers, you end up with 32 partial products. And then you can add them two at a time. This is what is called a Wallace tree multiplier. So you can add them two at a time. So in this case, if you have 32-bit, two 32-bit numbers, and you end up with 32 partial products, and you add them two at a time, you have 16 multipliers here. 16 multipliers that produce 16 results. So here you add them with 8 multipliers, which produce 8 results. So you add them with 4 here, produce 4 results. So you add them with 2, which produce 2 results, and then you add them finally with 1. Okay? And then you get, after all that, the 32 bits that you get here are your central 32 bits, and you have been doing shifting as you go through the tree over here, and here you have been using the carryouts of these additions to get the most significant bits. So in total, if you're doing the multiplication of 32 bit numbers, you have 1, 2, that's 3, 4, that's 7, 8, 15, and 16. So you have 31 adders. So you do it basically for a 3-type multiplier. You have the same number of adders minus 1 of the number of bits that you are multiplying. So you can see that what we were doing before, one cycle at a time, require only a single 32-bit adder, but this one requires 31 if we're doing 32 bits. So you can see the complexity and the cost. But this one is all combinational. There are no clock cycles. If you can manage to make this 32-bit adders fast using techniques like carry look ahead, which we looked at in your lab, which was the point of having you look at the timing of it, by using those techniques, if you can manage to make these 32-bit adders fast, then you get a lot of performance enhancement at the cost of a lot of additional hardware. And that is a decision that normally gets made in favor of performance, because we can put a lot of hardware on chips. The other benefit of this type of what we call parallel multipliers, because it's not on a cycle-by-cycle basis, is that you can pipeline them, a technique that we'll discuss in the next chapter. And while by pipelining, the latency or the delay or any specific multiplication of two 32-bit numbers in this example would take the same amount of time. If you're looking at throughput, which many times we are, which is not how long something takes, but the rate of completion of operations. And if we care about many operations, then the rate of completion becomes not only an acceptable, but a more attractive metric to improve. Then the rate of completion becomes much higher and your performance goes up, because you may be using, for example, once you are adding and you're done with this addition, you're done with those others while you are performing the other ones, but you're not doing anything with them. So why not pipeline and essentially put registers to isolate each layer, and while you're doing the addition here on the second level, you are doing the addition for the next multiplication that comes behind, and you're using all the others at the same time. So that's the idea behind pipelining, and that's how you improve throughput. So it's an attractive technique. Now that we have seen a little bit of the multiplication hardware, let's try to relate this to the actual ISA and the ISA of the ISA of the ARM that we're looking at, the LEGV8. We have three multiply instructions. So we have the MUL, and that gives the lower 64-bit of the product. Okay, that's what it yields. We also have a sign multiply high instruction, and that yields the upper 64 bits of the product, and the assumption is that the operands are signed. And then we have an unsigned multiply high, which gives the lower 64-bit of the product, and it assumes that the operands are unsigned. Because remember that the data path for the ARM that we're looking at is 64 bits. Now let's look at division. So what would be the algorithm to look at division if we call this we have here the quotient, which is our result, and the dividend, the number that we are dividing, and the divisor, that is the number that we are dividing by. And another part of the division is that we're going to have a remainder. Okay? So, of course, the first thing is to check that we're not dividing by 0. So the algorithm, just like the algorithm of the serial or multi-cycle multiplication, reflects the type of multiplication that you would do on paper, this type of division and the algorithm reflects what you would do on paper, or the long division approach. Okay. If the divisor is less or equal than the dividend bits one at a time, we have 1 bit in the result, and we subtract. Otherwise, we put 1 bit in the result, and we look at the next bit in the dividend. That is the long division approach. That's what you do in paper. An optimization is to use what is called restoring division, which is that we do not subtract. Do not subtract to avoid those subtractions. And if the remainder goes negative, then we add the divisor back. So that gives us some improvements in performance. If we have, so all this is refers to unsigned division. If we have signed division, we basically look at the absolute values and then adjust the result depending on the signs of the numbers that we are dividing, the sign of the operands. If the signs are the same, then we have a positive result. If the signs are different, then we take the 2's complement of the result. Okay? Making it negative. And this would be just like we looked at this before for the multiplication, this would be the algorithm and this would be the hardware. So notice that the hardware is essentially the same as the hardware for multiplication. Okay? Pretty much the same, with some changes. The point is that you can adapt this hardware to do both division and multiplication. So, and this is the non-optimized, the version 1 of the multiplication. So initially, the number that we're dividing by is in this register over here. And initially we put the number we're dividing by in the result on this register at the output of the ALU. And we go through the algorithm by looking at the bits and the shifts and the subtractions in this case. This is truly an ALU because it can do addition and subtraction if we're going to be using it for multiplication as well. And after we go through the algorithm that I explained in the previous slide, you end up with the result over here. So again, this is the number that you are dividing, the number you're dividing by on the left, and the result is here, and the algorithm is here. Okay? So the controller is going to be controlling this data path, giving the tests of the different bits at different times through the process. So you can see the algorithm here. Just as we optimize the multiplier, we can optimize it as well. And again, use the same hardware for both multiplication and division. So again, that's just a clever approach. Now, the other thing is that you cannot use a parallel divider like we can use parallel multipliers because the subtractions are conditional. but they can be made faster if you generate multiple result bits per step, but it still requires multiple steps. That's something to keep in mind. Now let's look at the two instructions that the ISA provides for division. We have a signed division and an unsigned division. By design, both instructions ignore the overflow and division by zero.